We've learned that a moving charged particle in a magnetic field experiences a magnetic force. We're going to focus in this video on what that magnetic force does to the path of that moving charged particle. Let's say, for example, that we have a positive particle in our magnetic field. And actually this positive particle is going to start out not in the magnetic field, moving to the right. It all of a sudden enters this magnetic field, and as soon as we have this moving charged particle in a magnetic field, we know it feels a force. We said that this particle was moving to the right, and those X's indicate that the magnetic field is pointed inward. Using the right-hand rule, we can determine that the force felt by this positively charged particle would be upward, and that's a magnetic force. Now, we know from all of our previous studies in physics that just because something feels a force in a certain direction doesn't mean that it immediately moves in this direction. So the particle wouldn't enter the field and then immediately move upward. Instead, the particle would retain a bit of its horizontal velocity, but then start moving a bit vertically. So maybe something along those lines. And if I were to draw that path, it might look something like this, till it gets to the point where it actually is moving vertically. However, once it starts moving vertically, that means that the force is in a different direction, because we use the right-hand rule to determine the direction of that magnetic force. If we instead have the velocity pointed upward and an inward magnetic field, that tells me that the magnetic force would be pointed toward the left. Just as before, this doesn't mean that our particle moves left immediately. Instead, it retains a bit of this upward velocity component as it starts moving left as well. You can start to see that this path looks somewhat familiar. Looks like a shape that we've seen before. Really, this path is a circular path because charged particles that move in a magnetic field move in a circular path. If this particle were to have started off in the magnetic field and perhaps an external force gave it a little push to get it to start moving, then its path would be a full circle as opposed to what we see here where that circle kind of went outside of the field all of a sudden. We've learned previously in physics that when something moves in a circular path, there must be some force that's causing it to move in that circular path. We called that force the centripetal force. In this case, it's the magnetic force that's causing it to move in a circular path. That tells me that the magnetic force is equal to the centripetal force. That's an important fact because that can let us know all kinds of things about the path of this charged particle. For example, if we plug in the equation that we've learned for magnetic force into this equation, as well as the equation for centripetal force, the fact that centripetal force is equal to mass times centripetal acceleration, or mass times velocity squared over radius, that can help us find the radius of the path of this particle. We can also find how much time it takes this particle to complete a full circle, otherwise known as the period of the motion. Sometimes we might be given the radius of the path and information about the magnetic field and need to find the velocity of the particle. All of these calculations really focus on the fact that the magnetic force is equal in magnitude to the centripetal force in this scenario.